Alright, so this is our marble roller coaster. We're going to start up here at the top and work our way down to the last feature. So we can see at the top, we are dropping from about 59 inches off the ground, which would translate, you'd subtract 3 inches because of the track height on the bottom. So really it's about 56 inches. And in our calculations, we used 51 inches from the ground. So we can see that friction is coming into play quite a bit there, as well as angular momentum. So which we did account for those, but it's really hard to get those accurate, especially with the normal acceleration in our loop. So it's really hard to account for because you get so much normal force from this loop that the friction increases a lot. So that definitely comes into play with our higher drop height. But yeah, we got our loop here, and we can see that it's not a constant radius, so it actually gets much tighter at the top here, which because it's going to provide more normal acceleration with v squared over rho. That radius gets tighter, so we'll get more acceleration, which helps a lot with keeping the ball actually in the loop, and it helps fighting gravity. And then our last feature, it's kind of like a jump, but basically it just comes up and then just stops. So we wanted to calculate it so that it would just come up and just barely land on the top of the track and then kind of sit down and stop right there. So you can see we have a really steep angle here, so that it does just kind of come up and just sit. And we have our stop here. So we wanted to switch it up a little bit from the original jump idea and just do something kind of creative and something that not any other group is doing. So yeah, that's our marble roller coaster. Alright, so this is our marble roller coaster math. So our math is split up into two sections pretty much. You have the paper part, which is more so just throwing ideas on paper. This is in this PDF here. This is the paper part. And then we have the Excel part that I'll go over in a little bit. So they do tie in together and they have references to each other. But first, we'll go over the paper part and just work our way down. So we can see we have our basic dimensions here, what our track width is going to be. So we want it to be 3 material thicknesses, our actual material thicknesses, our marble weight in English and metric units, and then our marble diameter. You can see here we have a rough sketch of the track. You can see here we have our hill, our loop, and then our landing essentially, as you saw in the video. So I do want to talk about our landing here and kind of where inspiration came from that. So if you've ever been to a, some kind of like outdoor carnival arcade kind of thing, you've probably seen this game before. It's called Bowler Roller. So the idea of it is you have to provide enough speed in the ball so that it can make it over the hill but not come back over. So that was kind of our inspiration for that. So I'll let this play through. And you can see that the ball has to have just the right amount of energy so that it can get over the hill but not roll back over. And so that was kind of our inspiration with this one, is we wanted it to have enough energy so that it can make it through the loop and then just sit on top of the track. So it's a pretty small, pretty small landing there. So if you give it too much energy, obviously it'll go flying over the landing. And if you don't give it enough energy, it won't make it to the landing. So we thought that was kind of interesting. And we did all the calculations with that in Excel. So here is basically where we started talking about friction. These are just some notes from discussing with the professor on how we would measure it. Same thing with angular momentum, just some notes here, some notes from the internet. And you can see here, angular momentum is referenced in column H and I on the Excel sheet. Friction, this value is located in cell C5 on the Excel sheet. So anytime you see this green writing, that references the Excel sheet. So that just tells you locations. You can see here we used an inclined plane with the ball on top of it, and the inclined plane was tilted. The angle was increased until the ball started rolling. Using that angle value, when it started rolling, we could figure out the rolling resistance slash friction of the ball. So the friction between the ball and the track. So how much the track has to deform to allow the ball to roll. So we have a free body diagram here with friction pulling up the incline, opposite of motion. And then we have our normal force and our weight. And using these coordinates, we can sum forces in the x direction. And using all that, um, we know that our friction force came out to that very small amount. And this was used in our calculations for energy. Angular momentum here, just kind of the same formulas and with locations. So you can see that's in Excel, column H and I, and then mass moment is column E and F. Here's our energy rearrangements for state 1 to 2, K and L, 2 to 3, N and O. 3 and 4 is Q and R. So just, again, just rearrangements to find velocity after the feature. Since here are sketches. 1 to 2 would be from, this diagram is also located on the Excel sheet for reference. So actually I won't even explain that. I'll just let you look at that on the Excel sheet. Here is our calculations for the jump slash landing. So these are also on the Excel sheet in columns T and U. Now let's go over the Excel sheet and we'll break that down. So here's our kind of just our constants over here. We have friction, gravity, circumference of marble in feet, which we needed for angular velocity to find the angular momentum. So we also did our mass moment calculation using the mass and the radius of the marble. You can see we got our mass moment there. And angular momentum calculation, we needed our inertia. And we just use this formula to calculate at each stage what the kinetic energy, rotational kinetic energy of the marble was. So you can see here we have our state 1 to 2, which would be from drop height to flat. And you can see we have our initial velocity. So velocity at state 1 would be 0. And our velocity at state 2 would theoretically be 12.84 feet per second. We figured out that this was actually a little bit lower due to the rolling resistance, and also the energy required to get the ball rolling was higher than we thought. So that plays into it a lot. And that's why we ended up having to drop it higher than anticipated. It's because of just how much energy is robbed, because the marble has to roll. So moving on to state 2 to 3, so flat to the loop. We have our entrance velocity and our flat, so V2 is the same as V2 here, so that's borrowed. And then we can see our velocity at the top of the loop should be 4.8 feet per second. Now this number is useful because this number is then plugged in down here, normal acceleration calculation. This calculation tells us whether or not our ball will drop out of the loop or whether it will remain in the loop as it's coming around. So using our tidal radius at the top of our loop right here and using our speed here, we can calculate our velocity, square root of rho, and this tells us that, well, actually it tells us our angular acceleration is less than gravity, which is almost true. So the ball does just barely make it to the loop. So actually this calculation is pretty close to accurate because I've dropped lower than ball comes off the track. So this calculation does hold up. This note should be screw my error there. Let's say 3 to 4. Borrow our 3, and so this is going from the loop to jump. This diagram's a little misleading as it was created by guys. Arrow. Also, state 4 is shorter than the loop, so the jump is actually at 1.5 feet, whereas the loop is at 2 feet. So it's misleading there. See, velocity at the top of the loop was v3, down, and then going down from 2 feet, and then coming back half. Lose velocity, so 3.8 due to friction. So you think that dropping from 2 feet coming back up to 1.5, you actually gain velocity, but you actually do lose it due to friction, which lines up with the real world. And then our jump, so we call that state 4 to state 5. Once again, we bring over v4, and then we have to use our angle of a jump here, which was 6 degrees. We have to work with radians because Excel works in radians. Using that, we can calculate velocity in the y and also in the x. So really our x is what matters here because we only have 2 inches to hit because that's our check width. So we know that it needs to travel less than 2 inches. You can see here our x distance in inches is 1.1 inches. So that's how far it will come up off the track. Well, that's how far it will come. Once it leaves the track, it will come 1.14 inches to the right, according to these calculations. And that is actually fairly close to the real world because it does land in that 2-inch span. So that's our math in Excel for the Marble roller coaster.
So, what went well for our project? First off, we have the CAD, basically no issues, and went very smoothly. Assembly, again, pretty much no issues. We actually learned a lot during this, but I'll get to some of that later on. The spacers as linkages between pieces, we just used them to keep the track connected, and went very well installing them. Sanding, again, went very well. We just did the sanding to make sure the track was smooth, and also made sure the pieces that we connected were also smooth so the ball would just roll freely and cleanly. Footers, we actually decided to add these on towards the end because when we first started doing it, it was pretty wobbly, so we just figured we'd tighten everything up and make sure it was solid. Loop geometry, I'll actually draw a picture for this one. So right here you can see that the radius was pretty large coming into the actual loop, but then it got pretty extreme here. It's not a very good picture, but you get the gist. And then it was pretty large again coming out. What went well on it was, with this being so large, or this being so extreme, it kept the ball on the track and it went well. This is why it's in the went well. And then stopping mechanism, this is just the piece that was on the very end, as you can see on the picture. And all we did was glue it on and really couldn't mess that up. That went very well.
What didn't go well? Our laser cutting, some of the parts, the laser didn't cut all the way through. So you might be able to see in the previous video that some of our pieces had like chunks of wood out of them, and it messed up the pieces basically because we had to kind of rip them out of the plywood. This, which can be a reason for some of our inconsistencies, imperfections in the wood along with the cutting, because the laser cut, we had to, again, rip out of the plywood, which would give us inconsistencies in the curves and just on the cuts in the wood. What also didn't go well was when we originally started putting the spacers as linkages for the pieces, we weren't using a pilot hole, and this led to our piece of the plywood to split. So we quickly learned that we had to use a pilot hole for our spacers. And then last thing that did not go well was we had to add spacers in the track because I'll draw a picture. So say we had a spacer here, track, and then didn't have a spacer for a good amount, the track would almost bow out a little bit and then come back in like that. Essentially, it's over exaggerated, but it would bow out, which led the marble to lose some speed because it would turn on a larger radius instead of a tighter radius. So we learned through testing that we had to add more spacers to have a tighter track.